All right, thank you. Well, about a year and a half ago, I gave a talk about where in the cell is my protein. And I've had some additions to that since then. So in 2005, when I retired, I had this project in Gina Turigiano's lab at Brandeis. I was sort of a super postdoc. And it was to use single molecule localization microscopy to locate a structure of interest through Gina. And what the idea was to make a single molecule localization map. And then to use that in the EM. Can you see my arrow here?
Yes.
Okay. To put a label on a target structure. And this is not a target structure, it's just an illustration. Anyway, that was the idea. So that you could identify a structure you were interested in by tagging it and using single molecule localization microscopy to find it. And of course, an additional possibility was to use this kind of mapping to determine where to mill a lamella in order to look at a particular structure within a cell. So the question is, where is that now? What is the possibility? What are the problems? Well, here we have a target protein, and there's a lamella we want to mill, about maybe 140, 150, 200 or so nanometers. And the trouble with fluorescence microscopy is that the point spread function is really quite large on the scale. And here, we apparently have our target dead in the middle of our point spread function. But in fact, when you collect the point spread function, the only thing you know is that your structure is somewhere in that ellipse. So you really want to narrow it down because the standard fluorescence is not accurate enough. And of course, you can do better with single molecule localization microscopy. Something seems not to be working properly. That's all right. It just going back. It's only about as big as this asterisk is. So I hope that's not portending what will happen. So there are many kinds of single molecule localization microscopies, and these are a few of them. And I'm going to talk about FPOM or STORM, which is what most people use. Now, the problem is if you have 3 fluorophores within the resolution limit, and you collect photons, you get a scatter of photons, more than this, but they're still scattered. If all of the 3 fluorophores are fluorescing, it's not possible to resolve them. But if only one is, we can locate it quite precisely. And basically what you do, if this is the distribution of photons here, you project them down onto the x-axis and you make a histogram plot. You can easily determine the approximate position of the peak and also the error in that peak. And that you can then plot a circle at the position that you've calculated, and you can determine the error as a radius around which you can describe a circle. And you know that your fluorophore is with high probability somewhere within that circle. And of course, then if you do that, this defines the resolution of the single molecule localization method. And so it might look something like this. And your fluorophores needn't be at the center. They can be offset. You know, they're most probably somewhere within this circle. Now, the real formula for this uncertainty, this error that defines the resolution, and it is precision, not accuracy, is the point spread function squared over the number of photons. The size of your pixel figures in this term, and the background figures in this term. And of course, n is the number of photons. So most people usually begin by quoting this. So the more photons you have, the more accurately you can determine, the more precisely you can determine the position. But the background can be quite an important term. And here are some just calculated examples. For instance, if the background is, you have no background at all, then the error, if you have a 0.9 NA objective, a point spread function, 250 nanometers, a pixel size, and about 500 photons, you could determine the error would be about 11 nanometers. If you have an increasing background, here you would have, let's say, 25 photons in the background, which is not a big number. You've already quadrupled the size of the error. That is, the precision is now much poorer. But still, you can see you can do much better than you can with just plain fluorescence microscopy. When I began on this project, we had decided to use cryo single molecule localization microscopy. And the first thing we did is to find out whether any fluorophores worked at essentially liquid nitrogen temperatures. And the answer was yes, they did. We tested PAGFP, photoactivatable green fluorescent protein, and it worked as well at liquid nitrogen temperatures for switching as it did at room temperature. There are a number of fluorophores. Here's the one we used, PAGFP, gives you about 500 photons per fluorophore. DRONPA is about 2,000. PAM-CATE, which is sort of a winner, is about 10,000. Now these figures all come from different labs, so they're not measurements done on the same instrument, so on and so forth. So there's sort of a rough guide. But in this case with PAM-CATE, this group had an error of localization of about 9 nanometers, which is about 30 times better than the Rayleigh criterion for resolution. So you'd think, well, more photons, the more accurately you can determine the location of your fluorophore. But there are downsides to having more photons, one of which is, for things like PAM-CATE, the time to complete an SMLM map grows, and it becomes quite large. It becomes many hours if you have to wait for that many photons before your probe bleaches and you can begin mapping another another molecule of PAM-CATE. So what can you do about that if the time is growing? Well, you could increase the laser power to reduce the time needed to collect data so that you don't have to wait as long. But there turns out to be a problem with that. And that is a strong laser beam can heat the sample, causing microcrystallization or melting. There's a recent bioarchives paper about using that to do time resolve. And the result of microcrystallization is your poor quality cryo-EM images. And at present, the number varies depending on which lab, but it's worth finding out. So something like 500 watts per square centimeter, you don't want to be above that, but it does vary depending on the sample and the lab. So if you're going to use a laser, it's worth finding out at which point your setup will, in fact, cause the microcrystallization. So the second downside is that for flavor proteins, when they're illuminated, generate toxic species, singlet oxygen and superoxides that can damage your sample. If my calculation for measurements based on this paper I referred to is correct, M. cherry generates about 3 reactive species for every 100 fluorescent photons. Well, at cold temperatures, there is some good news because fewer reactive species appear to be generated because these fluorescent proteins tend to generate about 5 times as many photons before bleaching. But the rate is not 0, even at cold temperatures, one assumes. You can't assume it is. You can assume it's better, but you can't assume you don't generate any such species. And of course, the diffusion of these species is reduced, but again, not to 0. So at cryo temperatures, a water molecule can diffuse about 60 nanometers in an hour, 600 angstroms. And an hour is the kind of time frame for making these kinds of measurements. So what we don't know is whether if you're tagging a molecule that you especially whose structure you want to determine, it would be nice to know whether you can do that safely or whether these reactive species might be somehow damaging your target. And I think there's some optimism that this isn't a problem, but no one has so far checked to make sure. So if that's your way of identifying your target molecule, it might be nice for someone to actually find out if that's a real problem or not. People suppose it's not, but as I say, no one's checked. So what can be done to reduce the exposure from the excitation beam? Well, collect more fluorescent photons with a higher numerical aperture objective lens. So the highest numerical aperture lens that's been used was had a numerical aperture of 2.17, and it was built into a cryomicroscope with a resolution error of about 12 nanometers using EGFP. So that sounds like that might be something worth exploring. The error should go something like 1 over the numerical aperture squared, should be about a factor of 6, and they actually achieved a factor of 5, which is a little less, but still, it's if you could collect 6 times as many photons, that might be a good thing. The trouble with is that when you have a frozen sample, the fluorophores are fixed. Their dipoles are fixed, and they don't emit spherically symmetric photons. In fact, the power radiated by a dipole emitter is more like a donut. And this drawing, which I've taken from the web, shows the dipole as this blue arrow here, and this is the radiation pattern. And as you can see, you get many more photons in the horizontal direction, and in the vertical direction, you don't get any. What does that mean? Well, yeah, so this power distribution looks like this. So this is the angle in 360 degrees, and this is the power. See, here's the whole of the donut. Here's the maximum direction of radiation, which is at 90 degrees. And this is about the width of an objective. So this would be the light that falls across the face of the objective. And you see, if you have a higher power objective, I don't know if you're annoyed by this thing that I see up here. It's blocking some of the slide. I hope not. anyway, you can see if you have a higher numerical aperture objective, you get a very curious distribution of light intensity across the face of the objective. And the point of that is that if you have a high numerical aperture objective, this is what the point spread function looks like. It's a donut when the dipole is pointed directly up the optic axis. If it's tilted a bit, here it's tilted 34 degrees or 51 degrees, you can see that the maximum intensity is pulled off to one side. This is the position of the fluorophore. This is the position you would get. You can see you can make an error. If the fluorophore is roughly at 90 degrees, you have almost no error. So if you, as Selvin and his lab did, you can determine the error that you get with the high numerical aperture lens. And you can see that you have an error depending on the number of photons. And of course, it's best when you're either at 0 or 90, and it increases with fewer photons. So these are not, when you're here, this is not an error due to photon counting. This is a systematic error. So you get systematic errors because these dipoles are fixed in space. Usually in room temperature, people assume that their fluorescent tag is free to spin, rotate about the axis, so that on the average it points in every direction, and you get a kind of ensemble which is well approximated by a Gaussian distribution. But when you have fixed dipoles, that needn't be true. And the other point is those errors were for in-focus images. When you have out-of-focus images, as you might have when you're using various tricks to measure the Z position of your fluorophore, the errors can grow quickly and can even be as much as 100 nanometers. Now, there is an optical trick to remove the problem, and the trick is to fiddle with the emergent light from the fluorophore so that the dipole radiation comes from the lateral component of the dipole. That is a component that's at 90 degrees perpendicular to your beam. And then you get point spread, point spread function that looks as if the dipole was not tilted. So that's one possible trick, but it involves modifications to the light path. The other one is to stick to a lower numerical aperture lens, like a 0.8 or 0.9, 0.7, something like that. Of course, you lose photons, but on the other hand, you don't have a systematic error. So it depends on what you do as to what the most important aspect of your setup is. Is it accuracy, or is it not so many photons? So the take-home messages from this part: keep the background low if you can. You will have a resolution that is 10 times or more better than the Rayleigh resolution. Higher numerical aperture objectives collect more photons and reduce the size of the point spread function, but the fixed dipoles at cryo temperatures can generate systematic errors in localization, and a lower numerical aperture objective or optical tricks can reduce, maybe not remove, but reduce the systematic error. Now, there are two recent papers doing the alignments. The first was by Dahlberg, 2020, and this was had an error of about 9 nanometers in X and Y, and about 35 nanometers in Z. Now, the question is, how do you align a single molecule localization microscopy map to a tomogram? Or was there a question? I heard a rattle in the background. No, okay. So this was done in 2 steps. So in the first step, what was done is to take the images from the fluorescence microscope, in which you can see the holes, the low mag holes in the EM grid, and you can use those to align the EM images, the low mag EM images, to the fluorescence images. And then in the second step, what they did was they used 1 or 2 dozen gold beads to align the low mag image that you've aligned to the fluorescence image to an axial projection of the tomogram. And using those 2 steps, they were able to achieve an XY registration of about 30 nanometers. The Z alignment was problematic. I'll talk a bit more about that. So the second was done by Hoffman et al. And this was the alignment of a 3D map, fluorescence map, to a FibSem map made of a high pressure frozen free substituted specimen. The sample manipulation, that is freezing, free substituting, and so on, introduced distortions so that the transformation was not a rigid body transformation, but was replaced by nonlinear mapping. And the result was about a 27 nanometer registration in one case, one example, and about a 90 nanometer alignment error in another. So the bottom line is the best registrations so far are measured in sort of tens of nanometers in X and Y. And aligning maps in Z can be problematic. And transformations needed to align maps may have to be nonlinear, even for lamellas, which you think of as sort of a rigid piece of ice, but you don't know that, and you may need to allow for a nonlinear mapping. So my final thing is to get back to the fish tank that I had at the beginning. Now, the front of the tank is curved, which acts as an optical element. So suppose you want to look at, make a SMLM map of a frozen blotted cell. Well, the cell sits on top of the grid, as you can see here, and this is a curved surface. So that curved surface, I will tell you, makes this kind of single molecule localization impossible. That is, you can't get a decent image of the fluorophores. You don't see a point. You see a blur if you see anything at all. And that's because this surface, which sticks up, in fact, distributes the light in ways that you can't compensate for by refocusing. So if this is your only situation, you have to look down on the top of it. To get an SMLM map, you'll need to use adaptive optics. And there are now objective lenses with adaptive optics built in. And although I haven't seen it done, by rights, they have enough adaptation that you should be able to compensate for the curvature of the cell. The other solution, which is to either look up from the underside or to flip the grid over so you look down on the flat side, the flat underside of the cell. And I believe this is what the Jensen lab did for their mapping, that they use single molecule localization mapping of frozen hydrated bacteria. I believe they look down on the flat side, so you avoid this problem. But even if you look through the flat side, there's still a problem. And this is the fish tank. So here you have, you are looking, this is your eye, and you're looking at fish in the fish tank. Now the rays leaving the fish are bent outward by the change from being in the high refractive index environment to a low one. So what happens is it appears that the fish has moved up this distance in the tank. So you see the fish is closer to you than the fish really is in the tank. Everyone's seen that. And so the distance that you observe, d prime, is what you observe, d is what you want. So the correction for that is that you want to multiply d prime here by the refractive index of the water. Well, the same applies when you get to look at cells even from the flat side. Now, when you begin, you're actually measuring the distance from this green fluorophore to the camera, to the objective lens. That's not what you need to know. You need to know this distance. So what you can do is you can put in an additional fluorophore, a second kind, that is on the flat side of the cell, and that solves the problem because you can measure the amount of movement that your, that your objective has to make to focus from here to here. What happens if you think about it is, here is your objective focusing, in this case, on the fluorophore, and here it is focusing on the flat side of the cell. So what you measure is this distance d. That's the amount you move the objective. And what you want to know is what is this distance? So you have to know the refractive index inside the cell. Now, the refractive index inside a cell is known for some cells or for a range of cells, and it varies somewhere between 1.355 and 1.39, depending on the cell type, depending on whether you're looking at the nucleus, the cytoplasm. In any case, if your fluorophore is, say, 3 microns deep, then the error due to this uncertainty will be something like 100 nanometers, which is maybe certainly too big for localizing a sample you're interested in, and maybe too big even to decide where to mill a lamella. And the point is that what might be necessary is to thin this specimen and then make the measurements. So the sort of thought was maybe the ideal solution for all of this is that you build your single molecule localization microscope into the FibSim instrument, in which you can, at some point during milling, you can make additional fluorescence measurements, so that this problem of wear inside the cell is reduced because you have a thinner amount of cell after you've milled away parts in here or in here. You then have a thinner sample. And so this error is no longer, you're not going through 3 microns of fluid here, but maybe much less, say a micron. And of course, if you do your fluorescence mapping, if you could do it on a lamella itself, the error would be tiny, maybe only 2 or 3 nanometers. So it seems that one way around a lot of these difficulties would be to have an instrument, a milling instrument, if that's what you're going to do, in order to remove this uncertainty due to the variation of refractive index within the cell. If here's just an example, if you want to have an accuracy or an accuracy of 30 nanometers or less, so you can mill your 150 nanometer lamella, then you need to have a maximum thickness that's under 2 microns. So getting an accurate measure of Z remains problematic. And as I said, building the microscope into the fib-sim, if you're milling lamella, might be the best way to go. And again, measurement of the Z position in a lamella would be off maybe 3 nanometers due to the inexact nature of your knowledge of refractive index in a cell. So the take-home message, I guess, from all of this is there's still a lot to do in cryo-EM. And I will leave the rest of the time for questions or comments or suggestions. Thank you.